clustering is a grouping of data where points in a group have high similarity or low difference. So why did I word it in this like kind of weird way? Well, the reason is because I want to kind of make it clear what our input is going to be. So our input is going to be a graph where we have a bunch of vertices and edges, and edge weights are going to either represent the similarity or distance between points. We're going to look at specifically both contexts. So in the similarity case, we want high similarity between points within a cluster, and in the distance case, we want low distance between points within a cluster. So that's what we're trying to do with a clustering at a high level. Obviously, in this paper, we're looking at fairness in clustering. So fairness was first introduced to the clustering context with like the seminal results of Hierarchical et al. Just a few years ago. And we're going to use a kind of variant of their definition of fairness. So in our definition of fairness that we're using, that was introduced by another work after Hierarchical et al., points in our graph are going to be colors. They're going to be assigned a single color, so it could be like red, blue, green, whatever you think of. And we're given this alpha threshold parameter, which is trying to mitigate the representation of a color in a cluster. So for instance, consider the simple two color case. So we have red points and blue points. And say we're given a threshold parameter alpha equals 1/2. That means that no color can make up more than 1/2 of a cluster. So for instance, if we look at this clustering, the two clusters on the left are fair because they're half red and half blue. No color makes up more than half of the cluster. On the right, however, those clusters are not fair. So this is not a fair clustering because there are some clusters that are not fair. You could consider an alternate clustering of this data set that is fair. If you look at each cluster, they have 50-50 red and blue points. So that's the notion of fair clustering we're going to be looking at, and it's a very common notion that is used in fair clustering literature now. Okay, now let's just take a quick step back from fairness and look at the other aspect of clustering that we're considering in this paper, which is the hierarchical aspect. So hierarchical clustering is simply an extension of the standard clustering problem, where instead of just creating a flat clustering, you're creating a tiered structure of clusters containing clusters. What we see on the right is an example of a hierarchical clustering. We have clusters that are contained within clusters. You can kind of traverse the structure up and down by looking at clusters of different resolutions. In addition, this encodes a bunch of different clusterings at different resolutions simultaneously. For instance, if you look at this hierarchy, you can look at all the two size clusters and you can see that they form a clustering themselves. On the other hand, if you look at all the largest clusters, the clusters not contained in any others, you get another clustering where there are only 4 clusters and some of them are larger. So it kind of simultaneously encodes a number of different clusterings at the same time. Some applications that hierarchical clustering can apply to involve problems in clustering, any standard clustering problem where you aren't given the number of clusters ahead of time. So you can just create a hierarchical clustering without knowing how many clusters you want. And then once you know how many clusters you want, you can extract that clustering from the hierarchy. Or you could look at the hierarchical clustering and see which level of clustering satisfies your problem the best. In addition, the hierarchical structure of a hierarchical clustering is inherently useful for a number of problems. For instance, consider like some sort of like search problem, where at the beginning of the search problem, you want to look at a low resolution. So you want to look at clusters that are very large to get like a high level idea of what's going on. And then once you pick a high level cluster, you can narrow your search by looking inside that cluster and look like traversing down the structure. So it's useful in search-like problems as well as a vast range of other applications. Okay, obviously in this paper, we're considering fair hierarchical clustering. So the definition of fair hierarchical clustering is pretty standard relative to the definition of fair clustering. You just extend it by saying a hierarchical clustering is fair if it contains only fair clusters at all levels of clusters. So for instance, in the hierarchy on the right, where there are 2 colors and alpha equals 1/2 like we had before, this hierarchical clustering is not fair because we have 2 clusters on the right, one with only red points and one with only blue points. So those 2 clusters are not fair, so this entire hierarchy is deemed not fair. On the other hand, if we look at this simple change that we can make, we find that this hierarchical clustering is actually fair. If you look at any cluster at any level, like a big cluster or a small cluster, they will all have 50-50 representation between red and blue points. And obviously, like this notion of fairness for clustering or hierarchical clustering generalizes to other values of alpha, as well as other numbers of colors. Okay, so that's the standard like problem we're dealing with. Just quick pause. Does anyone have any questions? No? Okay. All right. So a useful tool we'll be using throughout this is the notion of a hierarchy tree. So hierarchy tree is just simply a representation of a hierarchical clustering that can be used for things like analysis or just visualization of what your hierarchy looks like. So consider the hierarchical clustering on the left. To construct a hierarchy tree from this hierarchical clustering, we start with the leaves of the tree. The leaves are just going to be the data points of the input graph. So I've already drawn those out on the right. We've drawn the data points as the leaves of the tree. So to construct the hierarchy, we start by looking, or the next step is going to be looking at all the smallest clusters, the clusters that only contain individual data points. So in this case, all of these clusters are of size 2. And we create an internal node for each of these clusters and connect them to the leaves corresponding to the data in the clusters. So pretty simple, just a representation of the first level clustering just above all of the initial data points. And then we traverse up the tree as one might expect. So we look at the next smallest clusters, in this case, clusters of size 4. We create an internal node and we connect them to the clusters contained within these clusters, or the nodes representing those clusters. And we continue traversing up the tree with the next largest cluster. And at the top, we put a single root for the cluster of all data points. So we assume we always have a single cluster of data points at the top. So that's what a hierarchy tree looks like. Again, it's going to be useful for analysis as well as the visualization. Another important thing to note about the hierarchy tree is another name for it is a dendrogram. And one like common use of a dendrogram is that like is easy to conceptualize is the phylogenetic tree. So the evolution of species is represented with a hierarchical clustering tree. Okay, so that's what a hierarchy tree looks like. And now we can kind of get into what problem we're specifically attacking. So in order to evaluate the goodness of a hierarchy tree or hierarchical clustering, you can either evaluate that experimentally or theoretically. In our paper, we address both the experimental and theoretical sides, while we do focus more on the theoretical sides because that's the focus of our results. In this paper, I'm going to only be focusing on theory. If you're interested in looking at the experimental results, you can see our paper. Okay, so how do we evaluate the theoretical quality of a hierarchical clustering of a graph? So the way we do this is we evaluate it using an optimization function. So an optimization function for our hierarchical clustering is a function that takes an input, that takes as an input the input graph to the problem, as well as a hierarchical clustering, which we represent by the trait T. And it outputs some sort of value that represents the goodness of the hierarchy. So the first one we're going to look at is Dasgupta's cost function. So note that optimization functions are either going to be designed in the context where edge weights are similarities or differences, because obviously switching the context could make the function work very differently. So Dasgupta's cost function is defined in the context where edge weights are similarities. Dasgupta's cost function was introduced 4 years ago. It spurred a lot of interest in the idea of creating and evaluating hierarchy optimization functions. So it's a very prominent seminal work. And it's shown to have like a lot of nice properties and be very intuitive. So it's maybe the most interesting optimization function that we know of in theoretical computer science to say to approximate. So here's what the cost function looks like. Again, it takes the input graph and the hierarchy as inputs, and we're just going to sum over all the edges in the graph of the weight of the edge times this S of TE thing. This notation is actually pretty different from the notation we have in our paper. I'm just simplifying it for the sake of presentation. But so let S of TE be the size of the smallest cluster in T containing E. So consider this edge in our hierarchy example on the right. what's the size of the smallest cluster in T containing E? Well, that's the smallest cluster in our hierarchy that contains both endpoints of the edge, and its size is 6. So the contribution of this edge to cost is going to be its weight times 6. Now, say hypothetically that this edge is a very high weight edge. That means these 2 points are very similar. The contribution of this edge to cost is going to then be 6 times the edge weight. And relative to the data set size, right, there's only 14 points, 6 is a very large coefficient to have. So we would consider this to be this will be a very high contribution to cost because we're multiplying a high cluster size by a high edge weight. So this is going to be a very costly thing to do. And note that it represents the case where we have 2 very similar points that are clustered very loosely in the hierarchical clustering, right? And you don't really want that. So this is basically the idea of cost is trying to mitigate the number of times you have very highly similar points that are clustered very loosely in the hierarchy. As an example of a well-clustered edge, consider this other edge and say it's a very high weight edge, meaning that these 2 points are very similar. Note that this edge weight is only going to be multiplied by 2, which is actually the smallest coefficient you can have. So that will be considered a very well-clustered edge, and it kind of goes with intuition of what like edges being similarities, or what you want to go for in a clustering on a graph where edge weights are similarities. So to recap, cost is enforcing that very similar points are clustered tightly in the hierarchy. Okay, so again, cost is a very well-respected function. It's honestly pretty intuitive if you think about it. To me, it seems like the most intuitive, simple algorithm that is holistic, that captures the interaction between all edge weights in the graph on the hierarchy that you're evaluating. So given all this, if this was the entire story, we'd probably just use cost as our optimization function of interest. However, there are some problems. So cost is NP hard, as one might expect. Often these things are NP hard to optimize. But in addition, under the small set expansion hypothesis, which is just some widely accepted hypothesis in theoretical computer science, cost is not even constant factor approximable. So the best algorithm we have right now for cost is a square root log n approximation. So that's not great. Maybe not something you would want for like a practical algorithm. In addition, like the algorithms that optimize for cost are kind of like a little bit more complicated and less intuitive than one might want. So cost is a very nice function, but maybe if we want to have more practical results, we need to look into other functions. So that is exactly what we do. Another optimization function of interest in this paper is going to be Moseley and Wong's revenue. So this is also in the context where edge weights are similarities. And revenue looks a lot like cost. The simple difference is instead of multiplying it by the size of the smallest cluster in the hierarchy containing an edge, it's just like the complement of that. It's like the number of points outside of that cluster. So one might like realize pretty immediately that cost and revenue are dual to each other. So the hierarchy that optimizes cost is also the hierarchy that optimizes revenue. So obviously both of these problems are going to be NP hard together. However, they approximate differently. Revenue is constant factor approximable. We know a number of algorithms that do this, probably most notably average linkage, which is a very popular algorithm in hierarchical clustering. It's like very empirically successful and is very simple and intuitive. Average linkage approximates revenue to a 1/3 factor. So revenue to some extent models this very nice, intuitive, practically useful algorithm. So in that sense, I would say revenue is like both simpler and more practically useful than cost. The final objective function we're going to be looking at is Cohen, Haddad et al.'s value. So the main interest of this function for this work is that we're looking at a different context where edge weights are differences as opposed to similarities. So it basically, the input graph just looks different. And it's also a maximization function. And note that this value function looks exactly the same as cost. It's exactly the same function, but now since we're switching context from similarity edge weights to difference edge weights, it's going to be a maximization function instead of a minimization function. and it exhibits a lot of the same properties as revenue. Average linkage is a constant factor approximation for value. There's a number of other constant factor approximations, and it's just easier to design algorithms for value than it is for cost. So in this work, we're going to address all three of these optimization functions. We're going to get kind of simpler, more practical results for revenue and value, but a more like theoretically interesting initial result for cost. Okay, so just pausing right here. Does anyone have any questions?
Yes, I do. This is Ben Schneiderman, and I'm just wondering about the, let me to understand the notion and why this fairness idea is important. It would seem to me that in the case of two colors, you need to have exactly equal numbers of red and blue in order to ever get any fairness clustering. Is that correct?
In the specific example I've been talking about, that has been the case. So if you want your alpha threshold parameter tells you we don't want any color to exceed this fraction of the like population of a single cluster. So if you have two colors and alpha is 1/2, you have to have entirely equal representation between the two colors.
So
However,
that seems like an extremely unusual circumstance, and I'm just wondering, to get my sense of intuition, why the notion of fairness is included here, and when would I want to use this form of clustering?
Okay. So there have been a number of works that have looked at flat clustering with this objective. So one reason you might want to use a 50-50 representation is if you have like a population that's 50% male and 50% female, and you want to balance the clusters. Obviously, this neglects like some other aspects of data and people, but that is one instance where that specific case might be interesting. But we can also use other threshold parameters. So for instance, if we let alpha be 1/4, then you could have up to, sorry, 3/4, not 1/4. Then you could have up to 3/4 of your clusters being blue and 1/4 being red, or vice versa. So depending on the definition of this alpha threshold parameter, you can loosen the constraints of fairness on these clusters. Does that make sense?
That helps. So
yes.
I'm then wondering where the edge weights come from.
So edge weights are just the input. So your input
But
graph.
what do they represent?
Well, for instance, it depends on what your input looks like. So maybe you're trying to cluster like, what's an example data set that I can think of? There are definitely a number of data sets that we could use. So like, say you're trying to cluster like a population based off of like geographic location. Like you could think of like trying to make districts for like voting or something. And you have like this distance function between individuals because you want to like cluster them geographically. And you want to say either balance gender. So you could have two colors where one color is men, one color is woman. Obviously, this is a simplification. And you want to ensure that in every geographic clustered region that you introduce, there's not going to be like too many men or too many women. Like maybe you want to ensure that men don't make up more than 3/4 of the cluster, so that like there's still like women, female perspectives that are present in the voting of each like geographic region you construct. And you could also do this for different like numbers of attributes. So you could do it by race as well to just make sure that no race is like super underrepresented in any geographic region, things like that. Is that a useful example that answers your question?
Helps. Thank you.
Okay. Yeah, there's a number of different examples. I didn't prepare any off the top of my head. So like if you look into fairness literature, a lot of like just fair clustering algorithms use this notion of fairness, and they will have like a plethora of examples of applications. This work is the first to extend it to hierarchical clustering. Okay, does anyone else have any questions? Okay. Then I'll continue with our results. So the first results I'll be presenting are for both revenue and value. So again, kind of the reasons why I'm doing this first is because they're more practical, more easy to see the usefulness of them. And also the algorithms are simpler. Like we don't require any big strategies to achieve approximations with them. Okay, So I'm going to start by presenting a high-level algorithm, which, like at a high level, it's going to solve the fair hierarchical clustering problem for both revenue and value. And then I'm going to do a deep dive on like the differences between how we're going to optimize for revenue versus how we're going to optimize for value. So a high-level algorithm works like this. So say we have our data set on the right, and we're going to be constructing our hierarchy tree on top of this. So we're going to start with something that is in fair clustering literature is referred to as a fairlet decomposition. At a high level, a fairlet decomposition is just a small initial clustering that is fair. So you make a clustering of your entire graph where like each cluster is not too large and each cluster is fair. And so this provides like a good starting point for either creating a clustering or a hierarchical clustering. And it's a very standard strategy in this field of work. So for revenue and value, we're going to need two different assurances for how our fairlet decomposition works. Oh, sorry. First, what this looks like in our graph, a fairlet decomposition is just like the first layer of our hierarchy. So for instance, in the two color case, where alpha equals 1/2, again, this generalizes to other scenarios, but just for simplicity, two colors alpha equals 1/2, you might look at a matching between red and blue points. That might be your fairlet decomposition, but obviously for other cases with more colors or different alpha parameters, this can look a little more complicated. So for the revenue case, what we need to ensure with our fairlet decomposition is that the maximum fairlet size is little o of n. All it has to do is be sublinear in n. So these initial clusters, the building blocks for our hierarchy, can actually be quite large. They could be n to the 0.99. So that's actually a pretty interesting result, I think, because like it means that you can start with like very large clusters at the base of your hierarchy and like ignore what could happen theoretically below that. So I think that's just a really interesting result that kind of reflects something about revenue and like how nuanced it is in evaluating hierarchies. For value, we need a little bit more of a strict assurance. So for value to get our result, we need to ensure that our fairlet decomposition captures a fraction of the system value. So what is system value? That is not the optimum value of the system. Let's just quickly go back and look at the definition of value. When I say system value, I mean take this sum over all edge weights and multiply it by the largest coefficient possible. So the largest possible size you could have of a smallest cluster containing an edge, which is n. So the system value is really just n times the total weight of all edges in the graph. That's what I mean. It's like an upper bound on the optimum value in the hierarchy. And also when I say system revenue in the graph, it's going to look the same. It's going to be the edge weights, the sum of all edge weights times n. So that's what I mean by system revenue or value. Okay, so again, for value, we just need to ensure that it captures some, possibly not constant, but some fraction of the value present in the system in the first layer in the hierarchy. Okay, so that's how we start our hierarchy. I'm going to go into depth on how we find this fairlet decomposition shortly. But to finish our algorithm, what we do is we just run some unfair algorithm for hierarchical clustering on top of that. And this algorithm must ensure that it captures some beta fraction of the total system revenue or value. Again, this is not a beta fraction of the optimum revenue or value. It's a fraction of the total system revenue or value. Fortunately, a lot of algorithms that exist that are approximations of revenue and value show this as opposed to a simple approximation. So if we just run like one of these algorithms on top of our initial fairlet decomposition, it will construct the hierarchy like however it wants. And what we can show is that this algorithm, creating a fairlet decomposition and then running an unfair algorithm, achieves an asymptotic beta approximation for revenue and value. So basically, we have no asymptotic loss in the theoretical approximation for our revenue or value optimization functions, which I think is pretty cool. Now, of course, the thing that's swept under the rug here is how we find our fairlet decomposition for both the revenue and value optimization functions. So let's look how we do that. So for revenue, obviously the problem is a little bit simpler for revenue. Let's talk about how we make a fairlet decomposition for the two color case. So say we have this data set on the right with a bunch of red and blue points. Notice that red and blue is unbalanced in this data set. So let capital R be the number of remaining red vertices, which in this case is 10, and capital B be the number of remaining blue vertices, which in this case is 5. Say our alpha threshold parameter is 3/4, and we'll write that as little r over little r plus b, where little r and little b are like the minimum values we can have to like write out this fraction. So little r in this case is going to be 3, and little b is going to be 1. Note that this basically represents how many red and blue points we need in a cluster to have exactly a 3/4 representation of red points in the cluster. So if we have 3 red points and 1 blue point, then the number of red points exactly meets this threshold parameter. Obviously, it would still be fair if it was less than the alpha threshold parameter, but this is the idea of how we pick little r and little b. Okay, so the algorithm is pretty simple. You're going to be looking at the difference between the number of remaining red vertices and blue vertices. If this is greater than, this is greater than little r minus little b, which is always going to be 2 because little r and little b don't change, then we'll create a new cluster containing 3 red points and 1 blue point. Otherwise, we'll be creating a new cluster using big R minus big B plus little b red points and little b blue points. And then the algorithm ends when the number of remaining red and blue vertices is the same, or we can just do a matching to create entirely balanced clusters. So this might have been like at a high level a bit confusing. So let's take this algorithm through step by step. So, sorry, getting ahead of myself. Let's look at the difference between big R and big B. So to start, the difference between the number of remaining red vertices and blue vertices is 5. So if we look at this conditional statement, 5 is going to be greater than or equal to little r minus little b, which is 2. So because the first conditional holds, we're going to create a cluster using 3 red points and 1 blue point. Okay, and this is going to be the first cluster in our fairlet decomposition. Now we've updated our remaining red and blue vertices such that big R minus big B is now 3. We still have that that difference is still greater than or equal to 2. So we go into the first conditional statement and make a cluster in the same way using 3 red points and 1 blue point. Okay, so we've created 2 clusters for our fairlet decomposition. Now the difference between the number of remaining red and blue vertices is 1. So that's less than little r minus little b, which is 2. And so we go into the else statement in this case. So in the else statement, we use big R minus big B plus little b, which turns out to be 2 red points and 1 blue point. And we use that to form a cluster. Now, it's not inherently obvious maybe that this cluster is going to be fair, but if you hash out the math, you can ensure that this like a cluster made by big R minus big B plus little b red points and b blue points is always going to be fair. Okay, so we've created our third cluster, which looks slightly different from our previous ones. And now we're at a case where we have the same number of remaining red vertices and blue vertices. So all we need to do to ensure fairlets here, or fair, like small fair clusterings here, is we need to, sorry, my thing's in the way. We need to create a matching between red and blue points, right? So if we just pair up a red point with a blue point, that's going to be 50-50 representation between red and blue points. And obviously that's not going to pass our 3/4 alpha threshold. So this is how we create our fairlet decomposition for the 2 colored case. I'll just note that this isn't an algorithm we came up with in our paper. This is one that was introduced by Hierarchical et al. And we are using this to obtain our fairlet decomposition to start out our algorithm for the revenue objective. So this shows that we can complete our algorithm and have a good revenue approximation when there are 2 colors. For the general K color case, for certain values of alpha, specifically ones where it's 1 over some integer, we show that we can use a basic round robin strategy to solve it. I'm not going to talk about it here, but so basically using that round robin strategy, as well as this algorithm from Hierarchical et al., we can complete our algorithm for a vast number of possible input situations. So we get our asymptotic beta approximation for revenue. And that completes our result for revenue. Now we're going to look at our fairlet decomposition for value. So for value, obviously, we have a slightly more like restrictive constraint because we need to capture some fraction of the system value in an algorithm. So the way we're going to start our fairlet decomposition for value is we're going to just start with an initial simple fairlet decomposition. So just use the algorithm we introduced before for revenue to create an initial fairlet decomposition. Note that algorithm doesn't have any assurances on the goodness of the fairlet decomposition. It just ensures that we have like a relatively small clustering where all clusters are fair. So use that algorithm to create a starting point. Now we're just going to do a local search algorithm to try to locally improve the value of this clustering. So the idea is we're going to look at all pairs of same colored points, so pairs of red or blue points in the 2-color case specifically, and we're going to try swapping their membership in clusters. So for instance, if we look at those 2 oblong clusters in the middle of this clustering, and say we consider the 2 red points, we might consider swapping which cluster which red point is in. If you do that, you'll get a clustering that looks like this. Now, when we look at swapping these 2 points, we will only swap them if it increases the multi-cut weight enough. So in some sense, the value of this clustering is going to be represented by the value of the cuts that partition the clusters between each other. You don't have to think about that like that hard. Just think about like we're talking about how much the weight of the edges between these 2 clusters. We're going to compare that with the edges of the weights of the edges between these 2 new clusters. And so as long as that increases the weight of the cut significantly, we will swap the membership of those points. So using this local search algorithm, we just run it until we can't do it anymore, and we can show that it captures some fraction of the system value and is relatively efficient. I'm not going to talk about like what this fraction is, but it allows us to basically complete our results for value. So what we've shown is an initial algorithm that can solve an approximation for both revenue and value in the fairness context, given fairlet decompositions. And we also introduced ways to achieve these fairlet decompositions for both the revenue and value cases. So this completes our algorithms for revenue and value. All right, I'm going to pause right here. Does anyone have any questions?
I had a question. So in the revenue case, you were describing an algorithm to make the fairlets.
Yes.
I might be misunderstanding, but where does that even take into account like the weights on edges?
It doesn't. So if you recall, when I was introducing the high-level algorithm, all we need to ensure is that the maximum fairlet size is small. It's a sublinear in n. It doesn't, the fairlet decomposition does not have to say it's good at all in terms of revenue. It can entirely ignore the concept of revenue in order to complete this result, which is why I was kind of saying earlier that it's kind of an interesting reflection on what, like, how nuanced revenue is as a metric. Like, it kind of implies that for any hierarchy you want to create, fair or not, if you start with just a set of clusters at the bottom layer that are sublinear in n, again, that could be really large, that could be n to the 0.99. If you start with that, you can still get the same approximation factor by putting an unfair algorithm on top of it. So yeah, it's interesting that you point that out because that was very surprising to find when we were doing this analysis. Does that make sense?
Yeah, interesting. Yeah. Thanks.
Yeah. Okay. Does anyone have any other questions? Okay. So I guess this has been taking a little longer than I thought. I'm gonna try introducing our cost algorithm. But if it takes too long, I'm just going to cut it off. So our cost approximation algorithm, fair cost approximation algorithm is definitely a more theoretical result than a practical result. Specifically, the factor approximation we're getting is an O of n to the 5/6 log to the 5/4 n approximation. So it's really just an initial interesting result that proposes new techniques that one might use to make further progress on this problem or related problems. Additionally, it is specifically for the case where colors are balanced. We have 50% red points and 50% blue points, and there are only 2 colors. So again, this is just a very initial theoretical result, but we think it's interesting because it proposes a bunch of new strategies and also kind of illustrates, maybe not proves, illustrates how difficult this problem is to solve. Okay, so we'll just go into it. So at a high level, our cost algorithm is going to be a sequence of steps as follows. So the first step we're going to do is create some hierarchy. So we'll start by running some approximation for cost. So like the O of square root log n approximation algorithm for cost that I was talking about before, that does not consider fairness. So run an unfair cost approximation and get our initial hierarchy. So again, this might not be fair at all. We start with a very unfair hierarchy, and we're going to try to modify it to become fair with limited loss or limited additional cost accrued along the way. So the first thing we're going to do is we're going to simplify the hierarchy. We're going to simplify the hierarchy by just extracting one layer of the hierarchy. So consider this layer. This is a complete clustering of the graph, i.e. each point is in exactly one cluster that I've highlighted here. And we're going to basically ignore all other points in the hierarchy. So if you ignore all other points in the hierarchy, obviously beside the roots or the leaves, because that's necessary for the hierarchy, then we'll get a 2-tiered hierarchy with just the layer we've extracted from the initial hierarchy. Okay, in the next step, we're going to try to mitigate some of the bias in the system by taking really unfair clusters, so points with a lot of either red children or a lot of blue children, and we're going to merge them together. So for instance, these 2 nodes in the tree that I've highlighted on the right, they're really unfair because one is all red and the other has a lot more blue points than red points. So what we can do is we can merge them together and kind of like the extra red points and extra blue points will cancel out each other. And we'll get a hierarchy that looks like this. So we're getting a little bit closer to making this hierarchy fair. Now, finally, the last step we're going to do is we're going to transfer points between clusters to try to fix all of the remaining unfairness. So for instance, if we look at the cluster on the right and we take the 2 extra red points and move them to the other cluster, like as illustrated here, then we'll get a fair hierarchy. If you look at the clusters now, each internal node, which is a cluster, has half red points and half blue points. So basically what we're doing is we're taking our initial unfair hierarchy, simplifying it, merging clusters together to mitigate unfairness, and then transferring points to remove all the rest of the unfairness. Okay, so that's the high level idea. Now let's look at it in a step-by-step process. Okay, steps 1 through 3 are a bit simple, so I'm just going to present them on the same slide. So step 1, like I said before, run some not fair hierarchical clustering algorithm that approximates cost. So like I said before, we know that there exists a square root log n approximation. That's the best one so far. It might improve later on. And we'll get some sort of hierarchy that will be unfair. The next step is we're going to extract what we call a T maximal clustering. So T is an input parameter to our algorithm that will tune at the end to get our best result. So just view it as some parameter we've selected for now. So a T maximal clustering is found as follows. Look at the leaves of the tree and traverse up the tree. Anytime you hit a vertex, if that vertex is of size T or less, but its parent is of size more than T, then include it in the clustering and don't continue traversing up the tree. So for instance, in the hierarchy we have on the right here, if T equals 4, this is the clustering we would extract. If you look at each cluster in the clustering, it is of size 4 or less, and its parent is of size more than 4. So it cannot be included in the T maximal clustering. Again, note this is going to necessarily be a clustering in the graph, i.e. each data point is contained in exactly one cluster we extract. Okay, just as another quick example, and the one we'll be working with, if t equals 6, this is what the clustering would look like. It changes slightly because we can move a little bit higher in the hierarchy because t is larger. Okay, so that's what a t maximal clustering looks like. And like I was talking about before, we're going to use this to simplify the graph. We're going to ignore all other points in the hierarchy besides the leaves, the clustering, and the root. Okay, so this is our simplification, biggest simplification step. Then after this, what we're going to do is we're going to ensure that the cluster sizes are within a small range, like a factor of 3. So the ratio of the largest cluster to the smallest cluster size is 3. And so obviously this might not be the case at first. So consider maybe you could have t being 100, but you could still end up with a 2-size cluster in your t maximal clustering. This would be the case if you have a 2-size cluster and its parent cluster is of size like 101, something bigger than t. So you can still have a wide range of cluster sizes. So to mitigate this, we can just use a simple greedy algorithm where we merge clusters together. So let a small cluster be a cluster that is of size less than t. So that's a bad cluster. We want to increase the size so that we have this limited range. So we'll take a small cluster and we'll take another small cluster and simply merge them together. And we can keep doing this greedily until the current cluster we're working on is of large enough size, and then start with a new cluster. And we can just do this until all clusters are between size t and 3t. So for instance, on the example on the right, we have 2 4-size clusters, but t equals 6. So we need to fix that by selecting them and merging them together. And if we merge them together, we'll have a hierarchy that looks like this. And we can always ensure that the cluster sizes through this process are between 6 and 18 for our value of t. Okay, so this is the first 3 steps of the algorithm. And note that we haven't considered fairness at all. This is just basically a process to still have some structure from the initial hierarchy, but to simplify it to make it easier to work with. Okay, step 4 and after is going to be geared towards making this hierarchy fair. So let's just look at what at a high level what we're going to do. So to ensure that the middle level clustering in our hierarchy is fair, we want to ensure that there's a matching between red and blue points, like a perfect matching between red and blue points in the graph, such that all edges are contained within the same cluster. So what do I mean by that? Well, consider this cluster here, and we want to check if this cluster is fair. So what we're going to try to do is try to make a perfect matching between red and blue points. If there is a perfect matching, we can make a 1-to-1 correspondence between red and blue points and show that this cluster is fully balanced. So if there's a matching within a cluster, a perfect matching between red and blue points, that cluster is fair. And so this is the intuition we're going to be using moving forward. Okay, so obviously at this point in the algorithm, our clusters might be unfair. So we need to utilize 2 strategies to kind of encourage them to be more fair, to encourage this perfect matching to exist. And we're going to use 2 strategies to do this. The first is going to be a merge cluster process. So consider these 2 clusters on the bottom. We're going to try to match as many points as possible to see how balanced they are. And we're going to note the leftover points. So there's 3 blue points left over on the left and 2 red points left over on the right. To kind of reduce the amount of imbalance in these clusters, we can simply merge these clusters together and then increase our perfect matching size. And so this merging of these 2 clusters allowed us to reduce the amount of unfairness presented in the clustering. Okay, so that's one way we can reduce the amount of unfairness. Another thing we can do is transfer points between clusters, which is kind of a simple thing you might expect us to do, right? You could take the 2 red points from the right cluster and move it to the left cluster. If we do that, we'll get the following 2 clusters, and we can again increase our matching size in the same way. And now we're left with only 1 blue point left that we need to deal with. Okay, so those are the 2 ways we're going to do this. Step 4 specifically is going to be just a very simple step where we're kind of setting up for the merge and transfer process. So all we're going to do is we're going to label the number of what we call excess nodes in the clusters, and we're going to label the excess color. So what I mean by that, by that is a look at the cluster on the left, try to do your perfect matching. there will only be one remaining color, which is blue in this case. So the excess color is blue. And we count the number of nodes remaining. So in the case for the cluster on the left, it's 3. And on the right, it's 2. And the excess color is red. So we label all clusters in our graph with their excess and their excess color. Okay, so step 5 is going to be this merging process that I was defining before. So on the bottom right, I've created a point for all of the clusters in the graph, and I've colored it with the excess color and labeled it with the excess number. So for instance, for the point on the far left, that is a cluster with excess color red and excess 5. So these represent all the clusters in our graph and how we labeled them previously. So the idea here is we're going to take clusters with large excess and kind of merge them together by building components such that we can remove a lot of the excess, because the excess is the problem. The excess is the amount of unbalance. Okay, so we call a large excess cluster a cluster with excess greater than or equal to L. So L is just some other input to our algorithm. And in this case, in the running example we're going to be using, we're going to say L equals 4. So as long as a cluster has excess 4 or more, it is considered high excess. So this algorithm is going to run as long as there are high excess clusters of both colors. Okay, so as long as this is true, we start a new component by selecting a large excess blue cluster. So we take one of our blue points on the right, and we use it to start constructing what we'll call a component that will merge a bunch of clusters together. So we take our blue point and put it up there. Then we're going to do a loop to construct this component. So this loop is going to occur as long as the component is not too large, as long as there are at most 4 clusters in the component. And it's also going to only continue as long as one of the clusters in the component has large excess. So what we're going to do is we're going to add a cluster to our component that has large excess and is red. So in our running example, what we're going to do is we're going to take this 5 excess red cluster and add it to our component. And we're going to try to match as much of the excess as possible between these 2 clusters. So for instance, we could take 5 red points from the right cluster and 5 blue points from the left cluster and match them together. We visualize this as an edge between the 2 clusters, and we try to match as much of those as possible. And this reduces the amount of excess we have in these clusters together. Then we just kind of continue doing this as long as we can. So we'll take another red large excess cluster, match a bunch of the excess and reduce it. Now in the component, the remaining excess is red, so we want to switch the color of the cluster we're adding to the component. So we take a blue cluster and we try to match the excess, and we reduce the amount of excess in each of the clusters. So this creates components that have less excess than they did before. Since this component now has 4 clusters in it, we're going to stop constructing it because we want to limit the size of this component. And we're just going to start afresh with a new component. So we take our blue point, we try to match it with a number of red points until it has like no or little excess left. And now we're going to stop constructing this component because none of the clusters in this component have large excess remaining. And we can keep doing this with another component. And once we're done with the process, we're going to be left perhaps with some high excess clusters remaining, but they're all going to be of one color, because this process can continue as long as there's one of both colors. Okay, so this is how we merge clusters in step 5. And since we're low on time, I'm going to kind of like skip over the last step a little bit. Basically, at a high level, what the last step is doing is transferring vertices between clusters. We try to find a large number of clusters that we can remove a small number of points from, such that they still remain as balanced as they were before, and then distribute them across clusters that still need to fix their excess in order to like completely balance all the clusters in the tree. So again, that's a very high level thing. There's obviously a lot of nuances with this step that I was not able to go over. But if you're interested in this process, I would refer you to our paper. And after this, we can ensure that our hierarchical clustering still captures a lot of the structure of the initial hierarchy. It obviously incurs like a significant cost on top of that, but it still achieves a non-trivial approximation for cost, and the hierarchy tree is fair after we do this process. Okay, so to sum up our results, like for revenue and value, we get very close approximation results for the fair context compared to the unfair approximation algorithms at the time. However, there is now a new algorithm that achieves a better approximation for revenue. So that's something that we'd be interested in exploring in the future, seeing if this new unfair algorithm for revenue can be adapted to be fair. For cost, we create a new non-trivial approximation algorithm that introduces a number of new techniques. But there's a big gap between our approximation for the fair context and the approximation for the unfair context. There are a number of future directions one could do to improve upon this work. A lot of them are just like kind of improving the approximation factors for the fair contexts for a number of these optimization functions. Also for in the context of cost, fair cost, we don't know if the lower bounds might be like more constraining than the lower bounds without the fairness constraint. So it'd be interesting to explore the lower bounds for approximating cost when we want to ensure fairness. There are also a number of other different fairness constraints and contexts, like looking at Euclidean problems. That would be interesting. So yeah, those are some ways you could build upon our work. Thanks for listening to my talk.
Thank you, Marina. That was great. Anyone having questions? You can either post a question in the chat or unmute yourself and ask Marina directly.
So Marina, just yeah, like Leo said, a very nice comprehensive talk. You know, I think your exposition was really good, starting slow and motivating the context very well. I only have a very minor comment. So on pronunciation, in the fair clustering work, the first author's name is pronounced Chierichetti. This both CHs are pronounced like ch.
Oh, I was informed it was k.
Oh, you were informed? But, oh, okay. So
yeah.
If you had, then they must be right because they are as co-authors. Okay. Did somebody like Ravi Kumar tell you it is Chierichetti?
Yes.
Okay, that's interesting. Okay, I know Flavio for a long time, but I seem to have got his pronunciation wrong. Okay.
Okay. Cool.
Marina, there is a question in the chat.
Oh, in the chat. Okay. Chat.
Yeah.
Okay, so the question is it possible to have multiple fairness constraints? For example, with colors red, green, and blue, at most a fourth of the cluster is red and a fourth of the cluster is blue. Yeah, so that's something. So I think I know what you're asking. So like, can you have different constraints on the representation of different colors? I think that's what you're asking. If that's the case, that's actually something that's been, okay, cool. That's a more nuanced definition of fairness that has been studied in flat clustering literature. Our algorithms actually do pertain to that as well. They do work for that. I guess I kind of, we present them in a simplified way just to make sure it's like easy to present. The thing, there's like some small things about that might make it more difficult. So for instance, like if you take our revenue algorithm, we need to find a fairlet decomposition where the biggest fairlet size is small. Obviously, if like you could have a case, like say you have 99 red points and 1 blue point, maybe your fair cluster might be just a cluster of all data. So it might mean like your given input might make it such that the you cannot get a fairly decomposition of that size. Our algorithm actually, or the algorithm introduced by Chierichetti et al., just ensures that if there is such a clustering, a small clustering, then it will achieve that. If you want to look at problems where, like you're talking about, where there are different colors and they all have different fractional, like alpha thresholds, you get to cases where it's much more likely that something like that will happen. Like there are just a number of like edge cases that where you might not be able to achieve like a fairlet that is good. So our algorithms in general do extend to those situations, but there might be some edge cases where like you just can't achieve a good small fair clustering, if that makes sense. So there's some like nuances there. Yes.
Ben Schneiderman again.
Yeah.
Very interesting. I mean, you pushed the hierarchical clustering to new places with this fairness notion. And I wonder if you considered or have explored the idea of interactive visualizations to present these things so that you could see how poorly they're doing and then actually make manual adjustments of the kind you suggest, which would then allow you to see how close you can get to optimal performance. So it's simply just encourage that this seems like a good candidate for visual exploration.
Okay, so just to be clear, what you're suggesting is using a visualization algorithm for your hierarchical clustering problem is that to develop algorithms like you can use, or to evaluate them afterwards?
To show what their performance is like and how, as you vary constraints, you can see how much it makes a difference. I will send you a link. We had done a lot of work called the Hierarchical Clustering Explorer, and I'll send you the link for that. But it allowed the interactive exploration, which turned out to be extremely beneficial for the practical applications that we were working with users who began to understand where the dangers were. And so they began to be able to make better interventions. And that seemed to be, the integration, the balance of algorithmic and interactive solutions.
For sure, that sounds very interesting, and like it could be a really useful tool. I've never thought about that, so yeah, please do send it along.
That's why I'm asking. Okay, thank you. I'll send you a link. It's called the Hierarchical Clustering Explorer. It's on the University of Maryland site.
For sure. Thank you so much.
Okay,
yeah.
Thank you.
Marina, I have a question too. Have you considered the price of fairness for hierarchical clustering? I mean, in case center K median, K means objectives, it's pretty easy to come up with price of fairness results, so that is unbounded. It doesn't seem straightforward to me to answer this question for these objectives.
Yeah, so you're just talking about like the difference between like the optimum fair and unfair hierarchies.
Yeah, exactly.
I spent a lot of time trying to think about that and couldn't find anything. Maybe it'll be discovered one day. But yeah, like it's an interesting point is that all our algorithms compare our hierarchies to the unfair optimum, which means they might actually do better. They might have a better approximation for the fair optimum. But we don't know because it's really hard to characterize the difference between the best unfair hierarchy and the best fair one.
Okay, wait. So the approximation ratio is with regards to the optimal unfair.
Yep.
So you immediately get the result for the price of fairness, the approximation ratio. So you know that it's.
You have a bound on it.
Yeah. Because in the standard clustering objectives, this is unbounded. So I suppose that's great. So okay. Yeah, it would be interesting to compare to the optimal fair value. I'd say you might get a better ratio on that.
Yeah, for sure. So I mostly thought about this in the context of cost, where we get like obviously a pretty like high approximation factor, and like I find it relatively likely that like the optimum fair hierarchy is a lot worse than can be a lot worse than the optimum unfair one. And maybe that means that our approximation algorithm is actually much better than it looks. I don't know. I don't know how I would do that, but yeah, that's like something I spent a lot of time thinking about. Yeah, and obviously the bound we get from our approximation for cost for this price of fairness is a very loose bound. So it'd be still very interesting to explore that.
Thank you.
Yeah.
Any other questions? Okay, if there are no more questions, Marina, thank you again. It was a great talk. It was great having you today. Thanks, everyone. I'll send you the information about the next talk shortly.
Okay, thank you.
Bye.